Welcome in ENEA. I am Walter Gaggioli, responsible of the Solar Thermodynamic Engineering Laboratory. Today, ENEA hosts this dissemination event of the H2020 European project in Power. And now my colleague Monica Della Peguera, coordinator of the project, with a long experience for the development of the system for the solar components, which introduced to Empower project.
Okay, thank you very much, Walter. Welcome everybody. Welcome to this webinar of Empower project. Main idea of this webinar is to explain to you a big picture about concentrated solar power. Empower project is about this renewable technology. So today I will explain very briefly different things. First of all, I want to share with the wide audience, which is an European project, what we are doing into Empower project, and some key points to keep in mind at the end of this webinar. Most of you, well, all of you are European citizens, and everybody, every day in different ways, we pay taxes in our local regions, in our different countries, and this money goes to the countries, of the budget of the countries, but also to the budget of the European Commission. And the European Commission uses this budget for different things. For example, nowadays we know very well that they are using for buy vaccines, for example, for COVID, or to help to the countries to push the economy in the next months for go ahead from this pandemic situation. But usually, and also now, the European Commission has funds for make research and development activities. For this, the scientific society, the scientific community, and also a lot of companies, industry that has the innovation in their spirits, propose to the European Commission new ideas or new products or materials or needs that they require to go ahead with the technology, to go ahead with new things that can improve the life of everybody. So for this, the European Commission, with the assessment of the research community, prepare research and development programs. In this case, we use the European project, European program called Horizon 2020. In this program that finished last December, a lot of scientific people work in different topics about experiments about health, about transport, about batteries, about energy, which is the case of Empower project, social research activities, genetics, whatever you can imagine. This program gives funds to the research community and to the innovative companies or industries to make and to develop the ideas and have finally results to impact to the society. Nowadays, there is a new program which is called Horizon Europe for the next 7 years. And while everybody here, we are waiting for this new program to continue these research activities. How can develop an European project? It's very interesting because we have to know the ecosystem. We have to know people working in the technology that we work. Usually we know each other through scientific publications, through Congress, or from the collaboration that we have between us. Then all these people can have a meeting to make brainstorm and have to develop an idea. This idea has to respond the requirement of the European Commission in this case, for example. So the European Commission in our case say, okay, I need that you develop new materials to reduce the cost of energy because the people need to pay less for the energy. So then we meet together and to think what we can do for make this. Then we have to decide which technology we use, because also depends on the technology, the methodology, and also the final cost and so on will be different. You have to see also who makes what, which is the partner or the university or the research center or the industry make different things into the project and make like a puzzle. And each piece is very important. You have to put all together in a right way, write a big letter, a big proposal, and send this document to the European Commission and start a competition. Because a lot of people, a lot of consortiums, group of partners presented ideas, and the European Commission evaluate the ideas and say, okay, this is the best. So I put the funds in this proposal, and I give the funds to these people to make this idea at the end. So when you have these funds, you start the execution of the project and implement the methodology that you say that you will do. Start the experimental activities. Also make another things apart from this is about communication and dissemination actions. Dissemination could be to publish a scientific paper. Well, but this is very important because we share the knowledge with the scientific community and everybody increase the know-how, okay? But other very important is to explain to all the society what we can do, what we are making, and also how we use the public money coming from the European Commission to make these new things. So finally, of course, we have to achieve the objectives, and at the end of the project, we have to not to put all the results in the box. Instead of this, we have to exploit the results to try to make patents, to sell the patents, to open new companies, to try to increase also the employment or generate new jobs. So this is not the end of the project. The idea is to continue to exploit the results that we achieve during the project. So what about Empower? What about our project? We start to think about this in 2015. Some of the people that you can see here, we start to talk how to use new materials to lower the cost of the renewable energy. The consortium now is made by Mactel, Fertiberia, Nematia, Jocat, Corfer, and Bottler, which are companies. Mactel and Fertiberia are big companies. The other are small and medium enterprise, but all together works excellent in a very, very collaborative way. And we finally have very nice results. About the research center, which are the knowledge and the scientific community that also push this company to go ahead with these products are ENEA, the host of this webinar, FEA from France, Techniker, also a research center from Spain, and like that. There are no universities in this consortium, but it's commonly there are some universities. And sometimes there are technology platform associations. This is not the case, but we use these platforms, share some information with them, mainly in this type of activity of dissemination and communication. So we prepare the document and the idea between 2015, 2016. We make different meetings, face-to-face meetings, web meetings, to share documents and so on, and then we present this idea, and we have the funds and start the project in 2017. Which are the idea? Briefly, we develop 4 types of materials. In the next session, my colleague from ENEA will explain you which is concentrated solar power, but mainly in concentrated solar power, plants, you have emitters that collect the sun, And this light reflected by the mirrors is collected by a material or a component that absorbs this light and convert this light in heat. And this heat you can use for generate electricity, or you can store the heat to use the heat also, or again generate energy, electricity. So in this project, we developed new type of materials for mirrors. We developed polymeric basic mirrors. Also, we developed new type of coatings that can absorb the light and convert this light into heat for different range of temperature. So we can use in different type of application, from produce electricity, but also for use heat for industry, for example. On the other side, the third component was to try to find a light composite to reduce the weight of the structures. This is also we made during the project, and now we are working with a composite in a PV solar field. The idea to reduce the weight also implied to reduce the motors, the power of the motor that you need to move the mirrors, or could be also solar panels. And finally, the other material that we developed during this project was material that can storage the heat. So this is very important also because this type of technology is one of the technologies that you can storage energy in a heat way. So you can use this heat again as heat, or you can convert this heat in electricity. So it's very, very versatile, the renewable technology. So we start to work in 2017, and we are finishing. We finish next month. So during all these years, we make several experimental activities. We report a lot of documents to the European Commission showing which are our results and the evolution and the progress of the activities. This photo is our last photo of our last face-to-face meeting. It was in Brussels in January 2020, before the pandemic situation. So COVID-19, as you can imagine, changed our life all over the world, and also for this consortium, of course. So we start to make all the meetings by this type of ways, WebEx or Teams or whatever, using different platforms, Zoom, and try to continue with activities was a little hard because apart from, of course, personal situation, we have a lockdown in the cities, lockdowns in laboratories. Not all the person can go to the laboratories to make experiments. So thanks to the European Commission that we give us 6 months more to try to finish all the activities, that I can say that we will achieve this goal. So a little picture about one of our pilot plants that also my colleague from Actel will show in the next sessions. And only to stress that apart from COVID and so on, finally we achieved the objectives of the project. We have patents in the project, so I wish that these patents finally increase possibility to have new jobs and new opportunities for the people. And also we have a scientific publication that increase the knowledge into the research community. So finally, to keep in mind some things, but very important things as citizens. We are working under a big framework, more than the European Commission framework, is the Sustainable Development Goals. In our project, impact directly to the 7 goals related to renewable energies. This is a must. We need to deploy these technologies all over the world. There are different types of technology. Here we are talking about only concentrated solar power, but we have to push as a research community, but also as citizens, to put this technology in practice. The other point, of course, that all this type of research affect everybody. So it's very important that to continue this type of research. So also we have to push to have this type of funds coming from funding public funds or private funds. But of course, we need money to continue to work in all these activities. And the other point that everybody can participate. And this is very important to keep in mind that also as citizens, maybe you can participate in activities like this to learn about this type of technology. But also there are another kinds of activity that, well, not right now we can do because pandemic, but you can enjoy or join. In fact, this webinar was like a plan B solution. The idea of Empower is to have 2 open days. The idea was to open 2 laboratories and 2 pilot plants to everybody to see really a concentrated solar power plant and see what it works. But well, due to pandemic situation, we cannot do it. But this is the way that we finally decide to see to show you our results and the idea of an European project. So thank you so much and enjoy this webinar, and we are open to all your questions.
Thank you, Monica, for your kind presentation of the Empower project. I remember audience that can send your question in chat. In the end of this session will be a little space to answer the major question. Now, my colleague Luca Turchetti, that is the Italian delegate in the Executive Committee of the Solar Basis, and have a long experience for developing solar thermodynamic technology, will introduce you to CSP technology.
Thank you, Walter, for the introduction, and good morning or good evening, depending on where you are, to the attendees of this webinar, which, as you may have understood, is not addressed only to experts in CSP technologies, but on the other hand, is aimed at introducing the general public to these technologies. Because actually, when we hear people or media talk about solar energy today, they basically implicitly or explicitly refer to photovoltaics only. So this is a technology which is not known to the general public. This is why we wanted to include in this webinar also and start this webinar by a general introduction to this technology that is, compared to PV, is based on an older and, let's say, simpler idea, which was, you may know, be attributed to Archimedes for protecting the city of Syracuse from the siege of the Roman ships. And that idea is to use a set of mirrors to a wide and extended surface of mirrors to collect and concentrate the sunlight over a receiver in which we flow a heat transfer fluid, which collects with this energy, this solar radiation, in form of high temperature heat. And very important features, as I will show you right away, is the possibility of storing a part of all this heat produced for later use when the solar radiation is not available, like at nighttime or during cloudy days. So what do we do with this solar heat? Today there are several applications that are being envisaged, for sure at the research level, and to some extent also for commercial application. We go from directly using the solar heat produced in these facilities for industrial or residential applications, or even cooling, again, both at industrial and residential level. Or we can convert and collect this energy, this solar energy, into energy carriers like solar fuels, for instance, hydrogen, or also conventional liquid fuels, produced by using solar energy, or solar commodities. And we can use this energy to desalinate water and provide drinkable water in areas where the solar resource is abundant, but water is not. And last, but definitely not least, we can use this heat to produce power, and which this is for commercial application today the largest market for concentrated solar thermal technologies. And in this case, we talk about concentrating solar power. The idea, again, is simple in principle. The application is not so simple, not always. So we use the solar heat to feed a power block, which implements a power cycle, a thermodynamic power cycle, to produce power. This is basically the way we produce power today, but with the difference that we are not burning fossil fuels to produce power, and then we don't emit CO2. And the fact that we are using, let's say, conventional ways of producing power makes also this technology very grid friendly, and allows us to offer to the grid important services that can support the penetration of other non-programmable renewables within the electric grid. So today there are four main concentration technologies that are used to concentrate sunlight and produce high temperature heat. There are two line focusing technologies, the linear Fresnel reflectors and the parabolic troughs. In this case, the solar radiation is concentrated along a line where we place a tube in which we flow the heat transfer fluid. Another approach is the so-called point focusing, is the one implemented by the so-called point focusing systems, like the solar tower, in which we place a receiver and we concentrate over a high tower, and we concentrate the sunlight through a set of mirrors which are located in the solar field, all pointing to the same point. This is why we call it point focusing system, or parabolic dish systems. With point focusing systems, we can achieve higher temperatures compared to line focusing, but in general, these systems have advantages and drawbacks. I'm just telling you that today the market is widely dominated by parabolic troughs, which is by far the most mature technology, which was the first commercial plants were built in the United States in the 80s of last century, and also central receiver, which already have an appreciable share of the market and are being more and more important, especially for new projects. I would say the key feature of this technology is the availability today of consolidated commercial solutions for thermal energy storage that in existing plants go up to 17.5 hours at full rated capacity, which means that the plant in the right locations and equipped with the thermal energy storage can also, during the specific periods of the year, can operate around the clock. And for sure, as we will see, they can decouple electricity production from the collection of solar energy. Today, the key commercial option for thermal storage is based on a two-tank system and the use of a mixture of molten salts that can be used also at lower temperatures, can be used as fertilizers. So we're talking about a mixture that is not pollutant, is not toxic, it's environmentally friendly, and also very stable, which allows this system to have a lifetime of several decades. We use this mixture of molten salt in two tanks. We have a cold salt storage and a hot salt storage. During the charging system, when we have excess solar energy produced by the solar field, which is not used by the power block, we can charge the system by heating up the cold salt to the higher temperature and store them in the hot salt storage. We can do this by employing a heat transfer fluid, which goes into the solar receiver, is heated up, and then it is used in turn to heat up the molten salt. In this case, we have a different heat transfer fluid and heat storage material. And in this case, we talk about indirect storage, or we use the same fluid as heat transfer fluid to collect the solar heat and heat storage medium. In this case, we talk about direct storage. And this is I would say this is really the core of the value proposition of CSP. Thermal storage means dispatchability. This is basically the only renewable energy technology based on a non-programmable resource that is actually dispatchable and allows to decouple the energy collection and the electricity production. So it allows us to produce according to the demand, which this is the meaning of dispatchable, the objective dispatchable. And to better make you understand this concept, here I'm showing you that the power per generation in Spain, which is the country in the world that today has I would say the highest share of the existing installed capacity, and it started in building the plants in 2008. Here we compare the production of a day in July of 2019 in Spain, the production by solar photovoltaic and concentrated solar power. You see that basically the production of solar photovoltaic follows the availability, the daily availability of the solar radiation. While in case of concentrated solar power, we're able to modulate the production according to our needs. We can have a flat solid production for instance, according to this production profile during the mid hour of the day, but we can also extend the production at nighttime, which is not possible, as you see here, with photovoltaics. And because batteries are becoming more cost-effective and technologically viable solutions are available for a longer storage times. But today, if you want to go up to 17, 15 hours of storage, which means round-the-clock operation, you can do this only with thermal storage in CSP plant. So what do the present CSP plant look like? There are also other technologies, but there are basically two main types of plants. I would say a first generation, the one that represents the highest share of the currently installed worldwide capacity, is a plant that is based on a parabolic trough concentrator using thermal oil as heat transfer fluid, molten salt as heat storage medium, and a two-tank indirect thermal energy storage system. You see here a picture of a parabolic trough collector. Of course, I didn't mention, but these mirrors must move during the day in order to track the sun and follow its position during the day in the sky. Here is a picture of the storage tanks, a molten salt storage tank, and these are expansion vessels for the thermal oil. And another type of plant that is gaining an increasing interest, and we are seeing in new projects and recent project, especially a recent project, is the use of a solar tower, central receiver or solar power tower, in which we locate the receiver on the top of this tower, which can be also hundreds of meters high, and we flow molten salts, the same molten salts used for heat storage purposes, as I told you before, directly into the receiver, and we heat it up to 565 Celsius degrees. In parabolic trough system, the maximum temperature is roughly 400 Celsius degrees. So this new generation of CSP plant can achieve higher temperatures, which also entails higher turbine efficiency in the power block. Clearly, you understand that this technology is not suitable for all locations worldwide. This plant used only the direct component of the solar radiation, which means that basically we can build these plants in locations where the DNI, so-called DNI, direct normal irradiation, is abundant. and this entails a combination of latitude for sure, but not only that, also meteorological conditions are important because we cannot I mean, the cloudiness has an impact on the availability of the ENEA. As you see here, there are regions close to the equator which are not good for installation of the plant. Good sites are the deserts of Chile, Australia, deserts of the United States, the so-called MENA region, the Middle East and North Africa region, Southern Africa, some region in China, and the south of Europe, Southern Europe, especially Spain. As I told you before, many plants are there, south of Italy and Greece. This, of course, also reflects the availability, the current market for this technology, which is today we have a total installed capacity of 6.1 gigawatts, with 2.3 installed in Spain, and emerging markets are the MENA region and China, and also recent plants have been built in Morocco and in Dubai, especially, and South Africa, and Chile, of course, which enjoys the highest DNI in the world. This is a rather relatively young technology because we have seen basically the technology being deployed after 2008 with an annual growth rate of roughly 20% of installed capacity, and the growth has been rather steady, with other countries being included in this run for this technology year by year. What I want to tell you that basically we have 10 years, roughly 10 years, a decade of experience of working this plant, which means that there is still room for improving the performance of this plant and the figures and the efficiency and the costs. As you see, the costs of this technology are, on the average, still higher compared to other renewable energy technologies, but these are the average cost. We see that the minimum cost, we have the world record today is for an auction in Dubai, 7.3 cents per kilowatt hour of energy produced, are in line with other renewable energy technologies. For sure, the reduction of the cost is one of the objectives that must be pursued for the development of technology. But just to sum up, what is the value proposition of CSP? Dispatchability, offering of grid services. Besides producing electricity, these plants can actually provide services to the grid, like frequency modulation, and also support. This is very important. Thanks to the dispatchability of this technology, it can support the penetration of other non-programmable renewables like PV or wind. Another very important point is job creation. These technologies really involve the creation of several jobs in the countries where they are deployed, and with a very high share, up to 30% of local content, which is another very important CSP advantage and value proposition. So I'm really out of time, so I just want to summarize, to tell you that there is still the road must still be underwent to improve the efficiency of this plant and the cost effectiveness. For this, it's important to have research that today is involved both in improving the efficiency and cost effectiveness of the existing plant configurations, but also in developing a new generation of CSP plants. And we will talk about research today in the second session of the webinar. And finally, also, of course, we need support from the public support for this plan to win to outcome the issues that come from a low deployment rate that these plants are experiencing today. So with that, I thank you for your attention. Of course, the floor will be open for your questions. Thank you very much.
Thank you, Luca, for your interesting presentation. Before to go the second session, that will be coordinated by my colleague Anna Chiara Tizzoni, I would like to underline a peculiar aspect of the CSP technology. CSP technology, a difference of the other renewable energy technologies, permit to store the energy. Then the CSP technology could be an important instrument to reach the ambitious target of the European strategic energetic politic that was set last year. Now, my colleague Anna Chiara Tizzoni will coordinate the second session dedicated to the research activity ongoing on CSP technology. Thank you, Anna Chiara.
Thank you, Walter. Good morning, everybody. I'd like to welcome you all to this second part of the webinar that is dedicated to the research activities in CSP technologies. I am Anna Chiara Tizzoni. I am working in ENEA Casaccia in Rome as a researcher in the Solar Components and Plant Development Lab, and I am dealing with the study and characterization of thermal energy storage materials. So in this session, we will have scientists and specialists from ENEA, SEA, and MACTEL in Spain that are going to hold three presentations that are concerned with the status of the main research activities in CSP field in Europe. So if you identify potential questions or curiosity you may want to ask to the speakers, please write down in the chat box on the right of YouTube. And remember that we will have the question and answer time at the end of the session. So we can start introducing again the first speaker, Walter Gaggioli from ENEA, that is the head of Solar Technologies Engineering Lab. And today he's going to illustrate us the main research activities in CSP technologies studied and developed in the ENEA Casaccia Research Center in Rome. Please, Walter, you can start.
Thank you, Anna Chiara. Today I will have the task to present the CSP research activity developed in a frame of ENEA. ENEA is a public body operating in energy, environment, and new technologies. The mission of ENEA is that to support the Italian system in green energy transition. The CSP activities are developed under the umbrella of the Department of Renewable Energy and Technologies. And the history of the CSP technology in ENEA started in 2000 when the Italian government through the national project Solar Thermodynamic. This project had set as a target to develop the components and system able to use the molten salt in the solar field and the system to store energy. Before of this project, in the solar field, it was used the oil. With the maximum operative range, the work was 309 degrees. With this innovation, it is possible to increase the maximum temperature of the working of the solar field. Then it's possible to reach the efficiency conversion, solar energy to thermal energy, up to 43%. And in the same time, it is possible to increase the capacity of the storage, the energy, up to 2.5 times respect of the old configuration. The activity of the ENEA are structured in such a way to cover all the aspects of the development path. So there is present the lab stage, where are developed the single components that will be employed in the CSP commercial power plant. They are the experimental plant, able to test the components developed in laboratory in the condition like to the real condition. Then ENEA can be supported the Italian system or the European system in the construction of the demonstrator plant and in the transfer of the technology developed in the frame of his experimental facility and laboratory. The general target of the research activity on CSP technology ENEA is to reduce to increase the efficiency and to reduce the energy production cost of the CSP system. To reach these objectives, the activity is divided mainly in 5 lines of the research. Developed innovative components like receiver tube, coating, mirror surface, new heat transfer fluid, small-scale concentric solar collector. Developing system and components to realize system able to use the solar energy for produce solar fuel like hydrogen. Use or the third lines is better to use the solar field to produce heat, able to be employed in industrial process. The last 2 lines research, very important, is develop the thermal energy storage systems connected with the power block and the solar field, and identify the smart grid technology able to integrate the CSP in the grid with this great penetration of the renewable energies. Regarding the activity for developing the single components, it was already reached the important results. It was identified the solar coating able to work up to 550 degrees in the under vacuum receiver tube with a very low emission at 550 degrees, under 10%. Actually, the challenge is that to realize the new coating stable in air up to 500 degrees in such a way to reduce the capital and operative cost of the solar field. Regarding the experimental plant present in ENEA dedicated to develop the CSP components, the major experimental plant is the PCS plant located in a research center of Casaccia near to Rome. This plant, it is a little CSP plant where present all components of the real commercial plants, like solar field and storage system. The very peculiar characteristic of this plant is that to use the molten salt in the solar field and in the storage system. This plant is supported by different test bench like optical laboratory, receiver tube testing, and chemical laboratory to support the experiment activity under developing the single components. In power, use this component to test is a new receiver tube, evacuated receiver tube at high temperature. In parallel, for the developing of the small concentric solar collector in ENEA is present an accredited laboratory. This laboratory is used to develop and optimize prototype of the mini and micro CSP system, Fresnel and dish Stilling system. This laboratory is included in the circuit of the Kermac, that is the European circuit to test this type of the CSP plants. Regarding the chemical laboratory dedicated for the CSP technology, in this case, the challenge is that to identify the mixture of the molten salt, like to reduce the freezing point in such a way to reduce the operative and maintenance cost for the big CSP power plant, but in the same time to test is it possible to use the molten salt technology also for the small size CSP plant. It's an important aspect of this technology, this activity of this laboratory is also the corrosion test, where I identify the relation between the use of molten salt with the contact of the constrained material used to realize the single components. Regarding the second line of activity dedicated for to the target to use the solar energy to produce the solar fuel, the ENEA activities concentrated to develop the single components or chemical reactor can be used as solar energy to produce solar hydrogen. In particular, in this moment, the activity is concentrated to develop the solar thermochemical reactor to transform the water in the solar hydrogen, and like intermediate step, the solar reforming reactor to transform the gas methane in solar hydrogen. In this area, it was built and committed plant where it was tested that it is possible to connect the power, the CSP power plant that use molten salt as heat transfer fluid and the storage system at the same time with the membrana reformer reactor, that is the components used to transform or the gas methane in the hydrogen. At a low level, but is important research activity is that dedicated to identify the cycle, the chemical cycle that can be used to transform water in hydrogen. In this case, they are ongoing the research activity in the sulfur-based cycle. For this activity, the experiment activity is focused to identify semi-batch or setup for the verification of the optimized select process. Regarding the third activity, the possibility to use the solar energy for the heat industrial process in ENEA are present at the Mose plant, where dedicated to identify the interface system able to connect the CSP power plant that uses molten salt as heat transfer fluid with the industrial process. In the same time, it is under construction near to the PCS facility, a new facility, ENEA ship. In this case, we use different kind of the heat transfer fluid like siliconic oil or mineral oil, where it's possible to test the connection of the solar field made by the Fresnel collector with the industrial heat process. The plant will be ready in the end of this year. The fourth line activity is that dedicated to develop the thermal energy storage system. In this case, the research activity is divided in many sublines. One subline, important subline, is that dedicated to develop the thermocline storage system. Usually, in the commercial plant, there are two tanks for to storage the thermal solar energy. In this line, we study the possibility to use only one tank, where is a licensed thermocline inside of only one tank, with the reduction of the cost. There are different types of the thermocline. There are the thermocline that use only the molten salt, but there are also the thermocline that use pebbles and molten salt. In this case, in ENEA is present at the facility Reslac, dedicated for this innovation subline of the research. Regarding the other type of the storage is a research is focused to develop a new material for the phase changing material. In this case, it's important to identify the layout of the exchange area for different type of the changing material, and this activity is developed under the test facility ATES. It end for the storage system, sensible thermal storage system, there is the Solteca plant that is dedicated to identify or develop a new module made by the concrete. Concrete that can be additional with the phase change material or can be made with the waste material. In parallel, there is also the activity for the thermochemical storage. In this field, there are mainly two lines in the research. One with a very low level of the technology development. In this case, the activity is focused for identify the particular system of material that can be used for the thermochemical storage. The second line is for the small, dedicated for the small solar collector that work at a low temperature, 100 to 200 degree range. In this case, it was realized the SunStore plant where he developed the absorption thermal storage based on the zeolite material. The last line is that the research is the line dedicated for define the technology and model that can be used for to integrate the CSP technology in the smart renewable grid with the high penetration of the renewable technology. I remember you that CSP is characterized by the present thermal storage, and then these characteristics can be used for to increase the quote of the renewable energy in the power grid that share the energy in the whole house in Europe. The last slide is dedicated just to show some major project ongoing and the connection with the other research institution in Europe. As you can see, there is a strong presence of the Spanish research, but the CSP topic is developed more or less in all countries of Europe. At this time, I thanks for your kind attention, and I give the words to my colleague, Anna Chiara.
Thank you very much, Walter, for your talk. We are very sorry there were some technical issues on sharing your presentation, Walter, but it will be available later on the link of YouTube. So, okay, so you can now introduce the second speaker of this session, Pierre Garcia from CEA. Hello, Pierre. Good morning. Pierre is working as a research engineer, and in particular, his work is focused on the design and modeling of innovative components for thermal storage. He developed dynamic models for sizing and optimization of storage systems and participated to engineering, construction, and testing of experimental facilities dedicated to sensible and latent thermal storage units. So please, Pierre, you can start your presentation that will be focused on the main research activities in CEA.
Thank you very much, Anna Chiara, for this kind introduction. So today we try to present you the CSP research activity that we are doing here in CEA, France. So first, a short introduction of what is CEA. This research center, it's the French Atomic Energy and Alternative Energy Agency. It is based on 4 pillars. The first one is defense and security to ensure the strategic independence of France. Second pillar is nuclear energy for energy production, for the energy independence of France. Third one is technology research for the industry competitiveness. And these 3 pillars are supported by fundamental research with material science division and life science division. CSP research are done in the technology research division. And this division is divided into 3 main institutes. One called LIST on software, mainly on software engineering, LETI on microelectronics, and LITEN, which is the institute for the new energy and new materials for energy. So this LITEN institute has 4 departments. One on nanomaterials, other on electrical transport and battery storage, a third one on thermal energy and hydrogen, and a fourth one on solar technology. This last department is mainly dedicated to photovoltaics issues and development, and activity on CSP technologies are within the thermal energy and hydrogen department within 2 main laboratories. First one is thermodynamic and solar technologies, and the second laboratory with activity on CSP is the laboratory of thermal components and system. I am personally belonging to this second laboratory. Since I think 12 years now, we are developing activities on solar collectors. mainly for medium and high temperature applications. So first, we have worked on oil Fresnel solar plant using heat transfer fluid thermal oil that can be operated up to 300 degrees C. And this plant is for multi-purpose activities. So from this plant, you can generate heat, electricity, but also cold and tap water. We have a prototype in operation for this such kind of plant. The second type of solar collector that we have developed and work on is solar Fresnel plant, but this time with steam at heat transfer fluid and operated up to 450 degrees C, so higher than common thermal oil can do. And the third kind of solar receiver is a high temperature solar receiver for solar tower. And in this case, we are designing air receiver that are tested at the CNRS laboratories. So another important activity on CSP that we have in CEA is durability aspects. We have a lot of devices to characterize the properties of the solar collectors. For example, their specular reflectance, the absorption. We have also microscope to characterize the reflectors. And we have a large expertise on this topic, with also durability aspects with indoor testings. We can do accelerated aging and test under different conditions of temperature, humidity, irradiation, abrasion, and also salt content in the air. And we have also partnerships with outdoor testing platforms in Morocco and in France. Another topic on another CSP activity that we are working on is power to fuel. We are working on solar gasification of biomass to convert carbonaceous material into synthetic gas. This can have a lot of applications that you can see in this slide. And we are working with modeling. Here you can see modeling of the reactors, optimization and scale up of novel solar reactor for biomass gasification in the framework of PhD thesis that we are in collaboration with the CNRS in France. We also work on thermal energy storage. This is my part as far as I'm concerned, with mainly two types of storage technologies. First one is thermocline energy storage. We have long experience on dual media thermocline storage with oil as heat transfer fluid and rock bed as filler materials, with prototypes in Grenoble and demonstrators also on the platform in Cadarache, in the CEA site in the south of France. We also are working on latent heat storage with phase change materials. We have here like small scale lab test loop to see to investigate the phenomenological phenomena that can occur while charging or discharging phase change material storage. We also have in Grenoble a prototype storage system that I will talk a bit more in detail later. And we also have a demonstration with a free-stage storage in the south of France on our solar platform. We are also working on thermochemical energy storage systems with hydration and dehydration of limestone, but it is not presented here. So now I will go more in detail on the CSP activity on storage systems that we have performed within the framework of the InPower project. In this project, we are working on two types of PCM systems. First one is with high temperature PCM. We have identified aluminum silicon as a very good candidate for phase change material at high temperature. So it can be used, for example, in plants operated at about 600 degrees C to increase the temperature of the tank and the temperature of the fluid while discharging the storage system. So our idea is to use them as a top layer in thermocline tanks with encapsulated PCM. So as I've just said, aluminum silicon is a very good candidate, but it has a main drawback. It has the main characteristic is that it diffuse heavily in the container, so it can lose the properties of the PCM. That's why we have worked on developing protective layer, customized protective layers with a silica-based matrix in boron-nitroid powder. So to do that, we have first tested a wide range of anti-corrosive candidate anti-corrosive layers with aging tests, and to select what was the best layer adapted to aluminum silicon as PCM. We have developed a new coating. A patent has been deposited during the InPower project, and we have also done the validation with PCM in capsules similar to those that could be used in CSP plants. And then after aging test up to 600 hours at 700 degrees C, we observed no adhesion between aluminum silicon and the container. The layer is always continuous and no diffusion of aluminum alloy. So it's very good results for PCM capsules containing aluminum silicon. Second aspect that we have worked on in the InPower project is mid-temperature PCM. So in this case, we are talking about a phase change material adapted to direct steam generation. In the case of you are using steam directly produced in the solar field, and then you want to store steam at about 300 degrees C and 100 bars. In this case, sodium nitrate is a really good candidate. We have already in previous projects demonstrated the thermal performances of such storage systems with using sodium nitrate. It's a tube and shell, in this case, is tube and shell storage system when you have water and steam flowing within the tubes, and the tubes are immersed in a bulk volume of phase change material. One of the drawbacks of sodium nitrate is the low thermal conductivity. That's why we are using fins and longitudinal inserts to enhance the thermal heat transfer between the steam and the phase change material. As I've already said, we have already performed tests with such storage systems, but we lacked information about the durability of such storage technology. That is why we have done a new test with quite old storage system with the same material that was previously used 6 or 7 years ago, just to check if the performance were maintained. And we observed no degradation of the storage unit during the storage campaign compared to the first test campaign. And this allowed us to check the thermal performance again. We can see here on the right of the picture, you can see 4 consecutive cycles with here the charges are shown in orange and the discharge in blue. So the charge is done at partial load. They are lasting about 17 hours. while the discharge are done at full load. They are lasting about 7 hours. So one charge and discharge cycle is lasting 24 hours. And we have here 4 consecutive cycles with very repeatable conditions. Here you have a condition steam and water temperature at the top and the bottom in blue and in red. You can also see the saturation temperature here in pink, and the PCM mean temperature in the storage tank in green. And here below we can see also the PCM temperature at different levels of the storage system during the charge and discharge. We can observe very controllable, well-controlled and repeatable conditions with fixed pressure in charge and sliding pressure in discharge. To go further on the durability aspects, we also designed a new test facility called Duracell. The object here is to have accelerated aging with repetitive cycles, automated in automated conditions, to assess the durability of the heat exchanger, the tubes and fins immersed in sodium nitrate during a wide number of cycles. So because only in the literature you can find only oxidation on coupons, on linear coupons under controlled atmosphere in isothermal conditions, and we wanted to check if there is no degradation of the oxidized layer while melting and solidifying the PCM. That's why we designed this this facility, and also so we can test up to 4 samples of tube samples at the same time, and these tube samples are pressurized under 100 bars, so to reproduce the operating condition of a CSP direct steam generation plant. And we can do up to 3 cycles a day with this facility. And so we have removed progressively the samples, and then analyzed it with a microscope, also with a gas analysis and the salt analysis by spectrometry to identify the difference in the composition of the atmosphere of the salts and the degree of the oxidation degrees of the metals. And this test campaign showed no degradation again of the storage media and the storage tubes during the up to 1,000 hours spent at 310 degrees C, that is to say with liquid PCM. Then to complete my presentation, just a quick look of the pilot unit and demonstrator that we are operating at CA. This, I think, a big strength of our organization, that we have a lot of pilot units. For example, absorption machine, organic Rankine cycle machine, desalination machines, sensible heat storage, and our solar platform in Cadarache in the south of France, with here the demonstrator with Fresnel plant with oil, demonstrator of Fresnel plant with steam, and here of Fabric trough plant for pressurized water. Here, this is a focus of the platform using superheated steam with 3-stage storage that we have developed in the case of a project called Asolen 450. In this storage system, we have 3 stages. First one with a regenerator used to de-superheat the steam, a phase change material similar to those to this that we have studied in the InPower project to store latent heat of the steam, and a low temperature thermocline to show the sensible heat, to store the sensible heat of the pressurized water. Now, I would like to just to emphasize a new orientation of our of research at CER on solar thermal activity. We are not only working on CSP, but now we are also working on SHIP activity, that is solar heat for industrial process. The solar collectors and thermal storage systems are mostly the same, but for different objectives and different context that you can see here in this slide. On the left, this is the CSP world with the main conference solar PCs, and with the competitors like photovoltaics, and the main driver is the cost, as was well presented by Luca before. And here on the right, the difference with the SHIP world with solar in heating program of the International Energy Agency. The main competitor are biomass, and the main driver is not only the cost, but also the greenhouse gas emission reduction or ozone depletion reduction also. So this is not the same context, but mostly the same components or similar components. So just quickly, one project that we are working on in the SHIP activities of the CEA, it is a project called Friendship. The idea is that the solar heat is already used for agro-food industrial processes, mainly at low temperature ranges, up to 120 degrees C. But this project wants to demonstrate that solar heat can also have a good advantages and can be cost effective at mid temperature ranges, that is to say up to 200 or 300 degrees C. That's why we are here in this project combining a lot of technology adapted to solar heat up to 200 or 300 degrees C, and we will demonstrate it in Grenoble with a solar field on the roof of our building, and also we will test chillers, combined storage systems, heat pump that could be implemented in solar heat for industrial applications. I think that is all for me. Thank you very much for your attention. I think maybe we will have time for questions at the end of the session. Thank you very much.
Thank you very much, Pierre, for your interesting presentation. Thank you. So now I would like to introduce the last speaker of this session, Alvaro Sanchez from Mactel. Good morning. Good morning, Alvaro. Welcome. Good morning. So Mactel is a Spanish company that applies the most innovative solution to the design, construction, and maintenance of projects in the different sectors in which it operates. Alvaro was also involved in Empower project in the development and integration of innovative materials to increase efficiency and lower the cost of production of energy in the CSP technology. So the presentation is concerned with the status of the research activities in Mactel in this field. So please, Alvaro, you can share your presentation.
Thank you. Yes, I am Alvaro Sanchez, and I am working at Mactel in the research and development department of this company, which is aimed as EPC contractor, especially focused in southern of Spain. And we have been collaborating at Empower project, especially with the implementation of the demo site for demonstration of different innovations. The main objectives of the Empower project at Mactel site facilities were to study new absorber coating for tubes at medium temperature, study lighter structures performance, analyze the soiling effect to mirrors reflectivity, accumulative energy produced and temperature difference between loops. Also, there was environmental analysis and techno-economic studies, as well as track of modification to regulation. All these activities have been developed. Some of the final conclusions are already achieved, but not all of them, since the project keeps going and will be finished in the next couple of months. Here there is a brief presentation of the PV facilities at Mactel site, where we can see the light structures that were used. And also the effect of the anti-soiling on the PV panels that got this treatment. And we can clearly see that there is no dust on those panels. The total power of the installation is 16 kilowatts, and they have solar tracker and light structures, as I said. Later on, we will go further into more details. Now, I also want to introduce you the concentrated solar power facilities at the demo site. We opt for a Fresnel installation, which is a technology that is not so widely used in Spain so far. So it already has some innovative concept. And Mactel also think that this technology can be more developed in the future due to its capacity for self-consumption facilities where there is a heat demand.
Sorry, Alvaro, sorry to interrupt you. Maybe you can share your screen in the entire mode and you can change your slide manually. Sorry. Okay, yes, perfect. Thank you.
So this CSP facility produce 20,400 kilowatts per year per loop. There you can see the size of these modules. It's around 36 square meters per module and 3.5 meters height. And they can accept up to 30 bar and 400 degrees, despite the current facilities. The demo site is working at 110 Celsius degrees using steam as heat transfer fluid, or HTF. So we also have a rank turbine, or RC, organic ranking cycle turbine, for production of electricity. As you can see in the loop, there is also a diffuser for excess of heat that cannot be absorbed by the ORC, so we can dissipate this heat without causing damage to the circuit. Here you can see a picture of the actual facilities. This is the power block, and this tank is the expansion tank, and also we can see here the diffuser.
Sorry, Alvaro, sorry again to interrupt you. You can put the sharing in the full screen mode, please.
I think there must be a problem.
Sorry, because we are watching your okay. Yes.
Is
on
it
the
now?
top, on the right, you can put in the full screen. Yes, okay, that's it. On the bottom, on the right.
Yes.
Yes.
Here? Can you see it now? Okay. I am watching all the time. it's all the time in full mode screen, so I don't understand.
Maybe you are okay. Maybe you are sharing two screens. That's why maybe.
Oh, so are you watching now the one saying CSP facilities?
Yes, but it is not in full screen mode. You can try to go on manually, to scroll the slides manually, because we don't see
Okay.
them. Okay.
Let's see,
Okay,
because
thank
I am pushing the full screen.
Okay, thank you.
Thank you. Okay, so here we can see also the tubes assembly. These tubes have a special treatment done by Techniker, which is also another partner of the consortium within InPower project. These tubes require a special assembly methodology since they are delicate and can get cracked if not done by experts. Here we can see also the difference between innovative and conventional tubes. And this is a picture that was taken when the mirrors were being commissioned, so they were getting aligned. Here we can see the complete Fresnel loops. 3 of them are for InPower project, and they all well, one of them is a conventional module. The other one got special tubes with a special treatment made by Techniker, and the other one got special mirrors that were developed by Nematia. So here we can also see the control system of the facility, where we can track the temperatures of each loop, which is around 110 Celsius degrees during peak solar hours. We can also track pressures and other relevant information of the process. This is an automatic system that can run without special operation or any staff directly engaged. It only requires some annual maintenance, so it's a very automatized system. And well, regarding the activities to track the performance of the innovations, we, for the PV facility, we measured the power output of the panels to compare the performance of the panels with anti-soiling system against the panels, the conventional panels. We also did surface tension tests to check if there is a difference implication affecting the panels when you apply an anti-soiling product. And well, we don't have already all the conclusions. Studies keep going on, but we are observing that the coating of the tubes are increasing the absorption capacity, the heat absorption capacity up to 4 Celsius degrees. For lighter structures, we also realized that we saved time during the assembly and the transport. The cost of these structures is similar, it's not so far from the conventional metallic ones, so this can be a potential product that can be commercialized in the future once tested in power with good results. And regarding anti-soiling, it shows hydrophobic capacity, and it will lead to further developments with customization for each soil, which has some effect on the efficiency of this innovation. So that's all from my side. Thank you very much for your time. Cristina, can you hear me?
Okay, thank you. Thank you very much, Alvaro. Thank you. Can you hear me? Okay.
Yes.
Okay, I remember that all the presentation will be available on the link of YouTube later. So thank you very much, Alvaro. We have not questions at all. So if no one else wishes to add something, I think we can close this session. Thank you very much to all the speakers for your contribution, your attention and discussion. And the webinar continues with the third session that is focused on the CSP commercial plans. And I am now going to hand over to my ENEA colleague, Simona De Iulis, who will illustrate will hold the session with 4 presentations that are concerned with the most important commercial plans of CSP fields. Thank you. Okay, thank you, Walter.
Thank you. Now let's go to the last session, maybe the more interesting, because we speak of the commercial CSP plant. And please, I ask my colleague Simona to introduce the session. And please, I ask my colleague Simona to introduce the session. Please, I ask my colleague Simona to introduce the session.
Thank you, Walter. Ladies and gentlemen, good morning, or good afternoon, or good evening. Welcome to this third session of the Empower project. Welcome to this third session of the this session is focused on commercial CSP plans in Europe, with an eye also to the MENA region, so the Middle East, North Africa region, particularly Morocco. There are in the world now, we have heard this morning, there are around 6 gigawatts installed, and almost 2.3 of these are in Spain. And so I would like to start this section with this pioneer with the CSP plant in Spain. One of these commercial plant is l'Africana plant in Spain, and I would like to introduce Alvaro Sanchez to welcome back Alvaro to present l'Africana plant. Please, Alvaro, the floor is yours.
Thank you very much. I hope this time you can see the presentation. It looked like there was some issue before. Not about the full screen, but that I was picking a different presentation. This time we are going to go through l'Africana solar power plant. And here we have an overall view of concentrated solar power installations in Spain. There are 50 plants in Spain with 2,300 megawatts of capacity to produce electricity. Mainly, they are installed in the south of Spain, with Ciudad Real, Badajoz, Córdoba, and Seville being the regions with more capacity. This is, as previously explained by other colleagues, due to the fact that there is more direct radiation from, well, in this region of southern Spain. And here we start to visualize where La Africana Energía is located. It's in the province of Córdoba, and it's also, as already said, a strategic area with high direct radiation. It has a footprint of 270 hectares and electricity for 100,000 houses. La Africana is a 50 megawatts CSP plant.
Alvaro, can you hear me?
Yes.
We cannot see your full screen. That was blocked, the presentation. Maybe there were some technical issues. If you go through the presentation mode, could you please do the presentation mode in the light on the right lower corner? Maybe it's...
Oh, all right, sorry, let me try again. Can you watch it now?
No, just...
Not now?
Not in the presentation mode, but at least we can see your slide. Okay.
Can you see the plant, the Africana plant?
We see, of course, a small picture, but not in the presentation mode.
Okay, I have the full screen mode, so I don't know, maybe there is some technical issue, but I will keep going on if you can see at least the picture. So the Africana plant has 50 megawatts, as the majority of the plants that are installed in Spain. They have this standard size due to optimization analysis, and also due to the regulation factors. As you can see there, there is a solar field, power block area, and also there are a water swamp for the tower, for the refrigeration of the system. Also, there is a water treatment plant because the used steam has to be osmosized and requires very good quality to be used in the power block. Here you can also see with some detail how the parabolic through collector is configured. Other characteristics of the plant, there were more than 500 workers during construction. That was done by Mactel with TSK and Grupo Ortiz. It was a consortium of these three EPC contractors, and Mactel is now part of the consortium also to operate and maintain the power plant. And currently it gives jobs to 50 people. It has 2 pounds of 250,000 cubic meters, and it provides heat energy of 180 million kilowatt hour per year. Other peculiarities of this site, it uses as collecting heat fluid synthetic oil, which heats up to 400 Celsius degrees. And there is also another loop for salts, which heats up to 380 Celsius degrees. It has capacity for 7.5 hours of storage with 2 tanks. And well, there is obviously a connection to provide electricity to connect it to the high voltage substation. It also, this kind of plants comes with generator backup. So this is some small emission that it has for some backup purpose during a startup or backup, but it's not widely used. Here we can, well, you can see how the design of and the shape of these parabolic through collectors is especially designed to concentrate the solar radiation into the tube. It's the same principle as in Fresnel. You and in other concentrated solar power technologies, where you concentrate or try to optimize the efficiency of the system, collecting as much heat as possible. And this technology can reach higher temperatures than 400 degrees, but for these kind of technologies, the standard temperature is around 400 Celsius degrees. McTell is engaged in other projects where we are developing new generation of thermosolar technologies that can operate up to 580 Celsius degrees. But this is the conventional technology, which reaches 400 Celsius degrees for the moment. And here you can see how the heated fluid is transferred to the power block, where there is a heat exchanger that heat up the steam that goes to the turbines and produce electricity. Afterwards, there is a refrigerating tower, and also part of the heat can be deviated or bypassed to the molten salts, so we can produce in hours where there is more demand, but there is no sun availability, as it is at the early morning and last hours of the day, when there is demand at houses. So this demand is covered with, part of this demand is covered with this molten salts solution. And this we have here we have a greater detail of how this tank is constructed. And well, just some final thoughts about this technology, which, as we all know, is competing with other technologies as electrochemical storage systems or photovoltaic systems. But this technology is here to stay because it has a very special and unique characteristics that differentiate this technology from the rest, such as well, its maturity, its storage capacity with local equipment and local resources. We don't need electrochemical batteries or anything anything that cannot be easily obtained or purchased in locally. So the molten salt tanks are made of stainless steel. The piping system also is made of stainless steel, and it's made by let's say, basic equipment that so you don't need to externalize or outsource equipment, and this is good for the European development purposes. Also, it provides inertia to the electrical system as conventional combined cycles. This differentiates this technology from electrochemical batteries and is a positive factor also for CSP technologies. And well, of course, the storage capacity gives us flexibility to produce when the sun is not shining. And this will be very important in the coming years when there is enough availability of technology, of installed capacity of PV solar installations that are giving electricity during the peak hours, and there can be higher production than demand, and this electricity can be used in molten salt cycles or can be storage this energy to be used in periods when the sun is not shining. So we in Mattel, we think this technology has a bright future, as well as the rest of the members in Power Consortium, that we are in the potential of this technology. So thank you very much for your attention.
Thank you, Alvaro. I'm sorry to let you know that there was still a problem, so the presentation was fixed and freeze on the screen, but it will be available on YouTube channel. And I'll ask to you to stay connected for any question that arise from the audience that will be on our chat. But now we will try to collect all the questions together to discuss with the panelists at the end of the session. Now we move to Italy, so to the other sunny country in Europe where it's possible to install CSP plants. Actually, Italy was one of the pioneer for the innovative technology, together with the TRAF plant using as it transfers fluid the molten salt. And now we are going to see also the use of heat transfer fluid of molten salt with a linear Fresnel system, and a commercial plant in Sicily, and will be shown by Valeria Russo, that she's a research engineer with more than 15 years of experience in this field, and she's following ENEA, so an Italian National Agency for New Technology, Energy and Sustainable Economic Development, this technical assistance to the company building this plant. She was involved since the beginning at the main Italian CSP research innovation program. So Valeria, the floor is yours, and I ask to the audience to write a question on the chat box, and we will try to answer to all the questions after the end of the session. Thanks.
Okay, good morning to everybody. I am Valeria Russo and I come from ENEA. Today I'm going to talk about the Italian CSP commercial plants. First of all, we have to say that these commercial CSP plants in Italy are financed in a project financing mode with private structured finance, so now with public financing. The argument of this presentation is based on the description of the first plant that is called a Partano plant. Then more in detail, we enter in the technology installed in these plants. the performance analysis, and finally we talk about the second plant, called the Stromboli. Okay, here are some general information of this first plant. It is situated in Sicily, in particular in Partanna, where we can see here the position. The technology used in this plant for the concentrator is the linear Fresnel collector. As said before, the heat transfer fluid that flow into the solar field is molten salt. In the plant is present also a thermal energy storage system, and the capacity, the electrical capacity of the plant is equal to 4.26 megawatt. The APC is made by Fata, that is a part of the Danieli Group, an Italian group. Instead, the solar field is provided by the Fresnel, so from German, and the receiver tubes are provided by Archimede Solar Energy. Okay, here we can see more in detail the main characteristic of this plant. As said, the gross power output is equal to 4.26 megawatt electric megawatt at the reference site condition. The solar field, the concentrator of the solar field is based on the new generation of Fresnel collector with large scale. So the width of the concentrator is equal to 16.5 meters. The heat transfer fluid that flow into the solar field is the solar salt, the classical mixture of the molten salt with the 60% of the NaNO3 and 40% of KNO3. The thermal energy storage is of direct type, so inside the thermal energy storage is the fluid inside the thermal energy storage is the same that flow into the solar field. The system is composed by two tanks, the cold one at 209 degrees centigrade and the hot tank at the 550 degrees centigrade. And moreover, in the plant is present also a natural gas-fired salt heater in order to compensate the thermal losses when there is bad weather or during the night, and also in order to increase the electricity production within the permitted limit. Finally, on all components are installed an auxiliary electric heating system in order to maintain the temperature of all these components above the salt freezing point during filling and draining phases. Finally, the power block is represented by a solar steam generator, so with an economizer, an evaporator, and a superheater, and by a steam turbine based on a classical Rankine cycle with an air-cooled condenser. Here we can see a simplified scheme of the plant. So it's possible to see the solar field with the linear Fresnel collector technology. Here is the thermal energy storage system with the cold tank and the hot tank, the gas fire heater, and finally the steam generator and the steam turbine. Okay, now we go more in detail of the single component of the plant. We start from the solar field. It has a modular structure and consists of 9 loops connected in parallel, like is shown in this figure. Is 1, 2, 3. Each loop contains 14 solar collector assembly connected in series and arranged in 2 parallel rows in these ways. Some data of the solar field. For example, the overall length of the loop is equal to 806.4 meters. The overall area of the solar field is 83,203.2 square meters. And the total number of the tube receiver for the overall solar field is 1,782. And the total number of mirrors is 20,736. but the data more important is the optical efficiency of the plant, that is equal to 69.7%. As said before, in this plant, the flow inside the solar field is the solar salt. This mixture has a high freeze point. In fact, it started to freeze at 238 degrees centigrade and ends at 221 degrees centigrade. So it is necessary to maintain the temperature of the molten salt in every part of the plant and in all operating conditions above this value. First of all, we have to say that the salt are kept continuously circulating, even during periods without solar irradiation. And the thermal losses are compensated with the energy stored in the cold tank and partially integrated with the gas aerator. But in particular condition, for example, when there is a very low flow, or even without flow rate, for example, during the filling and the draining phases, it is necessary to use an electric heating system in order to create or maintain the temperature above the freezing point. For piping, valves, flanges, and other components of the plant are used heating cables. But in the for the receiver tube, due to the presence of the glass tube, it's impossible to install the heating cable. So an impedance system based on the Joule effect is used. Here we can see some example of heat tracing. Here on the piping, on the flange, on the valves. Instead, for the auxiliary, for the impedance system, it is the Joule effect is exploited, and using the tube itself, the receiver tube, as electrical conductor and a heating medium. So a voltage is applied on the tube, normally in the middle of the electrical circuit, so in this point. This voltage determines a current, and the thermal power is generated. In this case, the heating of the system occurs uniformly through the circumference and the mass of the tube. Now we have developed a simulation model in order to evaluate the performance of the solar field and in particular of each loop. Here we can see the trend of the thermal efficiency in the curve, the green curve, and the overall efficiency, the red one, of one loop. And this is the trend of the mass flow rate in the loop. We can see that the mass flow rate have to decrease when the solar radiation decreases. But we know that inside the solar field, the flow must be always turbulent. So it is necessary to impose a minimum mass flow rate. In this case, this value is equal to 0.1. And at these values of mass flow rate, sorry, 2 kilos per second, not. And at this minimum mass flow rate correspond a solar radiation of 100, more or less 180 watt per square meter. So the new trend of the overall efficiency and the thermal efficiency change in this way. Also, the trend of the outlet temperature changes because when we fix the minimum mass flow rate at the constant value, the outlet temperature from the solar field don't reach the nominal condition, so don't reach the 550 degrees centigrade, but it less of the nominal value. Here we evaluate also the trend of the temperature from the inlet. So during the along the loop length at the inlet until the outlet. And here is the trend of the thermal power of one loop versus the solar radiation incident on the collector aperture. This value of the loop thermal power is important in order to evaluate the thermal energy, the dimension of the thermal energy storage. In fact, we in this plant the useful storage capacity is fixed to 180.5 thermal megawatt. We know that the power output of the plant is equal to 4.26 electric megawatt, and the efficiency of the steam generator and the power block is equal to 0.363. So the solar field and the thermal energy storage have to provide to the power block a thermal power equal to 11.73 thermal megawatt. But as said before, as seen before in this picture, we can see that at the reference site condition, so with a solar radiation equal to 800 watt per square meters, correspond a thermal power for each loop equal to 4.87 megawatt. So we can say that we need less than 3 loops in order to satisfy the power required by the steam generator. And so in this case, we can say that the solar multiple of the solar field is greater than 3. All the other loop can be used for storage the energy. And then can we define the storage capacity of the thermal storage system as the number of the operating hours at nominal power in absence of solar radiation. And in this case, with this dimension of the solar field and this capacity, test capacity in megawatt, in thermal megawatt, we have a storage capacity equal to 15.4 hours. Okay, during the operation in the plant, we can see that there is a transfer of fluid from cold tank to the hot tank via the solar field. So, and this phase is called charge phase. So we can see in this picture that the level of the cold tank decrease, instead increase the level of the hot tank until there is radiation. Then we have the discharge phase. So there is a transfer of fluid from the hot tank to the cold tank via the steam generator, and so we have steam production, and this phase is called a discharge phase. Instead, in fact, the level of the hot tank decrease and increase the level of the cold tank. In order to evaluate the volume and the mass of the thermal energy storage, we have to evaluate two parameters. One is the mass flow rate from the hot tank for each megawatt to the steam generator, evaluated in this way. And the other parameter is the volume of fluid transferred from the hot tank to the cold tank, always for each megawatt of energy to the steam generator, evaluated in these ways. These parameters, the volume of fluid, changes in function of the hot tank temperature. In fact, the molten salt flow from the solar field to the hot tank only when the outlet temperature from the solar field is higher than 370 degrees centigrade. But the volume at this temperature is different, is higher than the volume at the temperature of 550 degrees centigrade. So here we can see the trend of this parameter in function of the hot tank. With these two parameters, we can evaluate the volume of the test, the total volume of the test in cubic meter, and then the mass of the test in ton. But we have to remind that this is the usable volume of solar field, because the final volume of the test must be written, because there is a minimum operating level that depends on the pump suction head in the bottom of the tank, and there is also another an upper level in order to mitigate the liquid sloshing. So the total volume of the tank will be greater than the value calculated with the previous data. Okay, all these evaluations are based on the meteorological data that is provided by the solar GIS. In particular, based on the DNI curve during the year. The year is represented the typical meteorological year. Under is the representation of the effective radiation that collected by the solar field, and it is calculated in function of the incidence angle, that in this case are two angles, the longitudinal angle and the transversal angle, because we are talking of a linear Fresnel collector. Well, now, so this plant is in construction, as said before, in Sicily, and in this moment, the construction is completed on the 4th of December of the 2020, and now the commission activities is ongoing. The salt already circulated to the power block, the pipelines, and the equipment, so the storage, the draining tanks, the steam generator. And just in these days, also 3 loops of the solar field are filled with molten salt. The next miles foreseen are the first synchro on June of this year, and the plant is foreseen that entering commercial operation at the end of this year. Now we can talk about the other plant, the Stromboli plant, called Stromboli. This plant is equal to the Partanna plant. It is situated always in Sicily, near Trapani. The technology for the solar collector is the same used in Partanna, so the linear Fresnel collector. The heat transfer fluid is the molten salt, and also in this case we have a thermal energy storage of direct type with 2 tanks, and the capacity of this plant is equal to 4 electric megawatt. Also in this case the APC is FATA, but in this case the solar field is provided by Saint-Cnim, the part of a CNIM group from France, and the receiver tube are provided by Wijin, a Chinese company. This plant is under construction. Most of the main foundation in the power block area are completed. The storage tank erection is ongoing, and half of the solar field mirror boxes are already assembled. For what concerns the grid connection infrastructure, we have that medium voltage cable from solar plant to the electrical substation and the medium voltage and high voltage electrical substation are completed at 60%. Thanks for the attention.
Valeria, and as for the others, I will ask to stay connected for the to answer some questions in case they will arise at the end of the session. Now that we see, I mean, the 2 countries in Europe area, so like Spain and Italy, we go to MENA. The MENA region is at the forefront of the most recent wave of construction projects, and particularly with Morocco, and that is hosting the largest operating CSP complex in the world, Noor Ouazzazate, with almost more than 500 installed capacity. And I would like to introduce Abdessamad Faik, full professor at Mohammed Senk Polytechnic University, and also recently a scientific director of a green park in close to the university, both close to the located to close to Marrakesh. Since I'm hearing some noise, I think this is maybe you should turn off your YouTube channel to not avoiding this. I would like to give you the floor and ask the audience to write the question in the chat box, and we will come later to you for any answer. Thanks.
Okay, thank you, Simona, for this nice presentation. Today, I will try to give you a general overview about the development of Moroccan CSP power plants. Okay, before, I don't know why I cannot pass. Sorry, I think there is some problems. You can see my screen?
I can see your screen. If you go to
when I am in full screen mode, I cannot pass the slides. I don't know if something is wrong there. Okay, now it's okay. Now
okay.
It's okay.
Thank you.
Thank you. Sorry for this problem. Okay, before to start to speak about the Moroccan CSP power plant, I want just to introduce my university and also the GEP. I think you are familiar with this company. Is OCP company. This company is Moroccan state-owned phosphate rock miner and phosphoric acid manufacturer and phosphate fertilizer producer. And this company decided like a few years ago to create the Mohammed VI Polytechnic University in order not just to make research in the core business of this company, looking for product innovation in fertilizer and also to treat some kind of problem that they are suffering, but also to look for some kind of or to do research in a strategic field for Morocco and Africa continent. And especially in sustainable development when we are looking for energy, water, and environment. This is like the main mission of the creation of the University Mohammed VI. The University Mohammed VI is divided for the moment in 5 campus. The main campus is located in Ben Guerir. Ben Guerir is a city that is located in the north of Marrakesh, around 70 kilometers. And here we have like the big campus that is oriented for applied research and the teaching of exact science. It's like the campus of Laayoune and the biggest one. But in parallel of that, they develop different campus. One is located in Rabat, is the Faculty of Governance, Economic and Social Science, where is studying now the future king of Morocco. And also in Casablanca, this is the headquarters of this company, OCP, and the idea is to convert it to Africa Business School that now is located in Ben Guerir, but will be moved soon to the Casablanca. And we have also the idea here that they are going to create a Mazagan Institute where they are going to develop or to have incubation, a platform for a startup company that's working in the field of chemistry. And today I am in Laayoune, and tomorrow we'll have like the official inauguration of the campus of Laayoune about African Sustainable Agriculture Research Institute. That already started 1 year ago, but tomorrow we'll have the official inauguration of this campus. This is like an image of the green city of Ben Guerir that we are developing around of the Polytechnic University Mohammed VI. This is the university, but you can see here that we have different kind of platforms that surrounding this university, like Green and Smart Building Park, Green Energy Park, and Data Center. Just to give you idea about this component, what we call them here, Living Lab. We have just a few months ago, we inaugurated the biggest data center in all Africa. Is occupying surface area of around 2,000 meters square, and is having like a capacity of 5 megawatts electric capacity to power nearly 800 computer cabinets. This will allow us to faster our research and calculation related with things that we are developing at the university. In parallel of that, we are developing in collaboration with RSN, like what we call outdoor platforms of the university. Here, what you see here are two real photos. The first one is Green Energy Park that was constructed in 2007. Later on, I will give you an idea about this park. And recently in 2020 was inaugurated the Green and Smart Building Park. It's occupying 12 hectares. Where we have like different kind of building constructs in different ways to study the efficiency of new materials or methods, and also the integration of renewable energies in these houses. And now we are working in development of green ash tuza, what means green ash to application. And this platform will be installed in Jordsvar, where we have the facilities of OCP companies. And the idea of this new platform is to develop all technologies related with the use of renewable energy to produce green hydrogen, green ammonia, and green molecules. Regarding the first platform that we have just close to our university, Green Energy Park, here you see a real photo. We have here what we call indoor laboratories that allowing us to develop different kinds of materials, and also we have platforms for characterization of these materials. Outside, we have two platforms. One we call it outdoor PV platform that's allowing us to test different kind of technologies of photovoltaic systems. And here is an outdoor CSP platform that's allowing us to also to test different components at pre-industrial scale of CSP technologies. And here the big area is around 4 hectares, is occupied by a CSP power plant that was developed for research. This CSP power plant is 1 megawatt electric. We are using here a linear Fresnel technology in the solar field combined with with oil as heat transfer fluid. In this case, we are using Delcotherm Solar E15. This power plant was developed with the Italian companies in Rai, and the solar field was installed by Soltigua. And this power plant is equipped with a thermal energy storage, where we developed new technologies that is alternative for what was present before molten salt to tank storage. In this case, we are speaking about thermocline. That means using just one single tank, and by natural stratification, we have the separation of the hot fraction of the heat and the cold fraction. And this installation is having 20 megawatts ton hour that is allowing us to store 4 hours to produce electricity during the night. The material that we are using in this case as storage material is magnetite ore, is just rocks as storage material. This project, this solution was developed with an European project that's called ORC Plus project, was coordinated by ENEA, by Walter Gaggioli. And the main idea of this European project was to make extension of the solar field in order to use the heat that is produced in this part of the solar heat to store energy in thermocline system. This is the first system at pre-industrial scale. We are speaking about system is having 20 megawatts hour ton, and here is around the volume of 180 cubic meter filled with 650 tons of magnetite. In parallel of that, we are having other European projects, mean water CSP, and the idea of this project was also to develop a robot that's allowing to clean the solar field with high efficiency and decreasing the water is used for this purpose. This is platform. This small power plant is allowing us to develop research at pre-industrial scale. That means here we have the flexibility even to use different kind of to change, for example, the solar field, or also to test some kind of tube absorber tube, or even to change the oil, or even to use other working fluid for the ORC turbine that we are using here. That means is flexible power plant that can allow us to test the different components at pre-industrial scale. If we are speaking about the commercial power plants in Morocco that we have, the first one was installed in 2011. This is like not belong to the what is developed by Mazen. This is like a integrated thermosolar combined cycle power plant that is installed in Ain Bani Matahar, is in the east of Morocco. And the idea of this power plant, CSP power plant, was used to be integrated in gas power plants. This is like the idea of this. This is the reason why we call it solar gas power plants. This is owned by the National Office of Electricity. Is occupying total area of 160 hectares. But and this normally this conventional power plant is using the natural gas as fuel. This is the pipeline coming from Algeria to feed Europe, and Morocco is taking this gas to produce electricity. That means we have a production of around 472 megawatts, and 20 megawatts is guaranteed by the solar field that we can see here. This is the photo of this power plant. That means in this case, we are just using CSP to be hybridized with conventional power plants in order to decrease the CO2 footprint of this kind of conventional power plants. The second or the big project that we have in the world, this Ouarzazate solar complex, is having a capacity of around 580 megawatts. This is like the scheme of the power plant. This is like you can see here. We have is composed by 3 CSP power plants. The first one is NOR1, based on parabolic trough technology with a capacity of 160 megawatts. The second one is NOR2 with a capacity of 200 megawatts, is also based on parabolic trough system. And the third one is based on tower system, that's NOR3 with a capacity of 150 megawatts. And in parallel of that, we have like different kind of PV plant that is installed around this installation with a capacity of around 70 megawatts. That means in total in this big complex, we have around 580 megawatts produced by CSP technology, and small part of it is produced by PV technology that is located in this area. This is like the scheme before the construction of the project. Here you see a real photo that recently was taken in this site, and you can see here the NOR1 with the capacity 116, NOR2, NOR3, and this is like the PV, and also we have here a small installation of the PV in this area. If we go in details in these power plants, we have the first one is NOR1 that was starting the production in 2015, is occupying area of 458 hectares. The generation of taker is Mazen, but also is the ONI, is the Office National of Electricity, and the capacity is around 160 megawatt electric, with an investment cost of 1,042 million euros. In this power plant is similar to the ones that we have in Spain, like Andasol 1 and Andasol 2, or the others in the United States, like SEG 1 and others. We have like a solar field is made by a parabolic trough system, and here we are using the downterm as a heat transfer fluid. The reflexive area of this installation is around 1,308,000 square meter. This huge reflecting area. That means all this land is occupied by this parabolic trough system to concentrate the beam line and to produce this 160 megawatts electric. The technologies that is used here for the thermal energy storage is the two-tank indirect technology that we mentioned before. Why indirect one? Because in the solar field, we have oil is used as heat transfer fluid. And in this case of the storage material, we are using molten salt. That means here we need a heat exchanger to change the heat that is coming from the solar field by the the oil to the molten salt. And the capacity, the storage capacity in this plant is around 3 hours, equivalent to 1,269 megawatt per hour. And just to give you an idea, this storage system is made of 2 tanks. Each tank dimension is around of diameter 46.5 meter in diameter and of height of 40 meters. Each one of these 2 tanks we can see here. And the temperature of the solar field and also the storage system is the inlet temperature is around 293 and outlet temperature is 393 of the solar field. And in the case of the storage system, we have this similar temperature. The price of the production of electricity in this case was in 2015 was a little bit lower than the price was at that moment in Spain, around 21 cents per dollar per kilowatt. But in this case, they achieved to have a cost of around 19 cents per kilowatt. After that, they moved to the second power plant is NOR2, is the same technology like the previous one. Just in this case, we have the capacity of the turbine is higher. Instead of 160, we have 200 megawatts. And the storage capacity also in the case of the other one, we have 3 hours. In this case, we have 7.3 hours of thermal energy storage. If you see the photos, like they looks like similar. Just in the case of the molten salt storage system, we have the same technology, but instead of having 2 tanks, in this case we have 4 tanks. That's just multiplicating the system by 2. That means, okay, we have 2 tanks, what we call them core tanks, that they reach temperature in the beginning of the day at 293, and when they are charged, they have a temperature of 393 that dissolves and is moved to the hot tank. And these tanks is having dimensions of diameter of 44.1 meter and height of 16.6 meter. As you can see here in the photo, it says of all the power plant that we have in the world, like in Spain and the United States, we see just 2 tanks of molten of the storage. In this case, in this photo, you can see that we have 4 in order to multiply the storage capacity. The third power plant was different to the previous one. In this case, we are using the technology of tower system. It's like the technology that was used in Gema Solar in Spain, but the other one was having a capacity of 20 megawatts. In this case, we are speaking about 150 megawatts. Is almost 7 times or more than 7 times higher in capacity compared to the first power plant developed in this category in Spain, Gema Solar. And this power plant was starting the production in 2019. And as you can see here, it's not like the other technology. We have parabolic trough here. We have just heliostat that they're constructing all the beam on the top of the tower. The tower is having a height of 247 meters. And in the morning, we start to inject, or when we are operating the power plant, we inject the salt from the cold tank to the top of the receiver to collect this heat and to be charged. But in this case, we are going to higher temperature. Why? Because in the case of the parabolic trough system, we have the decomposition temperature of the oil used in solar field is around 400 degrees C. But in this case of the power plant, we are not using anymore oil as heat transfer fluid. We are using the molten salt as heat transfer fluid and also as storage material. And at this moment, we are limited by the decomposition of the molten salt that we are using now in this kind of the power plant. And the molten salt that we are using is always the same, is based on sodium nitrate, potassium nitrate with a 60 weight percent, 40 weight percent. And the decomposition temperature of this salt is around 565. And this is the reason why we are using the maximum temperature in this power plant up to 565 degrees. What means that in the other case of parabolic trough, we have just 100 degrees C of delta T. But in this case, we can have higher efficiency because we have a delta T of around 265 degrees C. It's like the big advantage of this technology. In this case, we are able to lower the price of the produced electricity or levelized cost of electricity, and we have just 15 cents per kilowatt in this case, compared to the first one was around 19 cents. This is like the complex of what is that. We have 3 power plants, NOR 1, CSP, NOR 2, CSP, NOR 2, CSP, and NOR 3, CSP. But the first one is based on photovoltaic, just 17 megawatts. After that, the Mazin, they released this power plant that will be constructed soon in Middles, in other parts, because what is here, Middles now we are here. And the idea of this power plant was the first one in all the world to have a real hybrid system between PV and CSP. It's not like the case of Warzazat. We are speaking separate power plants, 3 of them based on CSP technologies, and the 4th one based on photovoltaic technology. But in this case, we are speaking about a real hybrid system. That means we take advantage of both technologies to decrease the price of the produced electricity. And the idea here to construct 2 power plants, each one of them having 400 megawatts, and with a tariff about 7 cents. You can see here is almost is more than the half of the previous price achieved by the NOR 3. In this case, we have like 7 cents per kilowatt of produced electricity. This tender was already chosen that EDF with Green of Africa and Masdar, that will be the main companies responsible of the construction of this power plant. And I hope soon that the construction will be launched. As conclusion, I think CSP technology provides cost-effective dispatchable renewable electricity, because if we are comparing this CSP technology with other technology, that means it is like the unique renewable electricity that is dispatchable. And this thanks to its thermal energy storage system, because in the case of the PV or the wind, we need to have like some other solution to store the electricity, like pumped hydropower or even batteries. But in all these cases, when we are combining these technologies with other systems of storage of electricity, we are increasing the cost of the produced electricity. CSP technology can be hybridized with other conventional fossil fuel power plant, like the case that I was giving you to the power plant that we have in Morocco in Ain Bani Mabhar in Jarada. The Ouarzazate complex with a capacity of 580 was successfully constructed here in Morocco, and now is producing 580 megawatts of electricity. And also now we have like this hybridization between PV with CSP that even can decrease further the cost of the levelized cost of electricity. But in case we need to develop next generation of CSP, I think now there are big projects in the United States to develop the third generation of CSP power plant based on power system. And in case of using the nitrite salt I was showing you before, the idea there to use chloride salt in order to reach higher temperature, higher efficiencies, and to decrease the temperatures. This is all from my side. This is my emails, and I will be happy to answer to your question, and also to have your email if you want to have some partners from Morocco. Thank you very much.
Thanks a lot. Now we'll switch back to the European funded project through the Research and Innovation Horizon 2020 program, and but with the project that is called Horizon ST, so which means implementation of the initiative for global leadership in solar thermal electricity. This European project is led by Stella. Stella is the European Solar Thermal Electricity Association, so it's the voice of solar thermal electricity in Europe and MENA region, and is Brussels-based industry association and representing the interests of both industry and R&D members involved in the STE sector, and with the main action line of promoting the role of STE in decarbonizing the mainly the European power sector, but also providing a wider vision of concentrated solar thermal technology to adapt to political realities, acting as a bridge between EU institution and industry stakeholders, and finally as acting as a competence center for the implementation working group within the Strategic Energy Technology Plan of the European Commission. And the set implementation plan for CSP, which is called Initiative for Global Leadership in Solar Thermal Electricity, was adopted within the set plan at the end of 2017. And it's a guiding document for sector with both targets from cost and innovations, so also with the research and innovation point of view. And the main goal is to keep the CST and CSP, whatever you would like to call, global technology leadership, and rebuild a home market in Europe. I will give the floor to Marcel Bia, the General Secretary of Stella Association, and also coordinator of Horizon ST project. Marcel, the floor is yours.
Yeah, thank you, Simona. I assume my slides are now visible, right? Hello. Yes.
Yeah, there's your slides are visible, but maybe you have double screen. And
yes.
And okay, in this case, if you go through the presentation mode on down right.
You mean
right?
I have
yes
instead of the slideshow, the display setting, and then what?
No, you go to the slide to this display sheet. I mean, yeah, that one slideshow. If you go to that, oh, I don't know. This is what you should see in one screen, and the other one you should have the.
Yeah, which is I see also that I have a.
Doesn't matter.
But Simone, it's not so important. I think the essence of what I want to say is maybe regarding the project. So indeed, as you said, this project is born and funded by the set plan. As it was born in the haze of European approach to research and innovation, and indeed the original and still the only, let's say, objective of this project is to preserve, to defend the technology leadership in CSP, as it was said in those years, as of 2017, in Europe. This being said, the reality is different. The reality is that this project is eminently, very clearly policy-oriented project. What does this mean? This means that this project tries to find a way to show that the technologies, also CSP, is not competing with other technologies in the high stratosphere of, let's say, pure markets, or as according to costs, or in the according to the technological performance. This is not true. The reality is that they are competing to which extent a technology matches what is perceived by a country as matching its national interest. And to approach this kind of things, to approach this kind of dimension, as I say, we have developed, let's say, a kind of a strategy. We say we will approach the situation in specific countries, not in all the countries of the European Union, but in specific country, what we call relevant countries, the policy environment, and try to show that from the research and the development perspective, but also from the industry perspective, these countries, we want to suggest to them that maybe they should take a fresh look at the technology CSP that we like to call today CST. I will come back to that maybe in the question and answer section. That there is more at CSP than building 50 megawatt power plants that they were originally built on the continent in Spain. So here again, the key features of the project. This is a competence center. Well, this is all this is to embed the project. As I said, it's policy driven. It's not research project. It's policy driven project, to embed it in the logic, in the logic of the set plan, and you know that there were many industry initiatives, as they were called, over the last years, and these initiatives were then feeding into implementation plans. A lot of paper to be done by the industry, and not all were happy about paper, but no euro was flowing, and And officially, and even more than officially, this project has the ambition, modest ambition, to support European countries, especially those who are a kind of who should have an obvious interest in looking at CSP, to go through the legislative, institutional framework conditions that will make CSP happen in a country or not. So it's about opening doors for trying to suggest the best, let's say, to open the door to projects. Currently in Europe, there is no open door for CSP. I will come back also to that. There is a lot of R&D activities ongoing, but the R&D activities, if they are not backed or supported by what we also call the home market in Europe, is something that might go wrong. So we identified, as I say, relevant European countries, and of course there is not a scoop when I say Spain, Italy, Turkey as the Mediterranean country first, but also potential importers. You remember there was always this idea from desert tech times to today. There is the idea that if Europe was one block, it would make a lot of sense to use the potential, the solar potential of the south, and to bring it to countries that have not this kind of resources. So we identified this country around three, let's say, criteria: either the solar resources themselves, also what I call the natural capabilities, or they have really excellent research capability. They have guys that understand a lot about this technology, or or there are companies there that are able to be involved in the value chain of CSP technology. And the last one criteria, of course, is to look into countries from where we knew from the times, when we were discussing in Europe this kind of cooperation mechanisms. So again, exporting from the south to the north. We know that a number of countries in the Central Europe and North, as of Germany is of course an emblematic example, are very advanced in renewable policy, but they are lacking, of course, solar resources. So this being all said, here a quick, we have a few but fine partners, and ENEA is one of them, besides German, DLR and PSA, and METU, Turkish. I always underline the quality of support we got from METU that we looked into as the first country. And then some words about what do we understand by the R&D perspective. Now, we try to assess in those countries these kind of things. Are there at all technological R&D capacities in this country? Are there labs? Are there units, academia also working on that, or just not? Are there how are these kind of entities, let's say research entities, are working, knowing that most of the research is done by companies themselves? So we're talking about public funded entities, and is there a structural dependency on funding from national funding agencies? How does it look with the direct contracts with local or not local industries? How do they look like about the participation of research entities in international projects? You will all know better than I do that there is an old vision and ambition of a European Commission, and the European perspective is to align, to better align, to avoid redundancy, and to have European R&D centers cooperate. And I tell you, in my view, seen from today, this is what works much easier, even if not perfect, than having the industry achieving larger alliance. So we have in the research in the reports that we will provide for this country, we try to also to point at the facts to which extent R&D is operated under different government. We know that this is, everybody knows that, but we try to see there if there is a kind of our dependency or things that are pushing for or are favorable to some developments around CSP, or are there blocking elements. Well, the whole, this part of the message for each country, we will conclude in those R&D perspective, let's say, reports, that if there is in a given country such an excellent potential or excellent level of research, but no cooperation, no sufficient cooperation with the industry, there is a threat on funding. This will not go forever. Then, especially public funding is allocated to something that has no market, let's say, and home market translation. So this is incidentally, I'm saying incidentally, because this is an old story also, that in a lot of projects, some of you know about Heu Solaris and Desfera, and a number of projects have already tried to detect redundancies in research activities, improvable alignment of these research lines on industry needs. All this is really different in all the countries, and we're trying to bring a kind of let's say a new light, or maybe a little bit more policy-driven approach to that. Now, I'm flying over this the slides, and the industry. Now, what is the industry perspective? Is, well, as I said, very simple. I mean, this is really not a science fiction or a scoop to say all starts with policy making and policy at all, political level. So the two things that conditioned that making, that are really delivering a specific market, is not the technology, is not the cost. This is first a national energy policy strategy, and translated into national regulatory framework. These two things together open or close or keep close the market for a given technology. And this is not new. This is not, let's say, CSP, think of nuclear in France or so. This was not the cost that played a role. This was not that in those years, the technological performance, but this was a kind of perception of national interest that was then bulldozering everything into regulation and delivered this wide highway for nuke in France. And so it's the same for PV and wind. I cannot be so long about that, but it is, believe me, not just because of the cost and that those technologies developed, but there were and there are still a number of dimensions in this that match some policy, let's put it like that, intentions. So this market for CSP, or with T is used, I'm sorry, for technologies, is also the first result, if you want, that we try to hammer on as of today compared to 2017 when we started the project. Of course, there is still some countries, and here it's very clearly Spain and Portugal too, that where CSP or CSP plus PV power plants with a large storage capacity makes sense for the power system. But we will go a little bit more in details into that in the questions, maybe in the second part from our presentation. But there are, besides the power market, besides the electricity market, really a number of companies and applications that may be developed by industry responding to these what I call opened doors. And I was listening earlier to, I think it was Valerie's slides, or maybe I'm wrong, where somebody said that the ship, relation between ship and CSP is stronger than ever. And yes, I can only insist on that. There is, and I push even the ball further, there is let's say a glooming perspective about integration of the solar industry along various types. This is not PV against CSP or against or high temperature against low temperature. A lot of companies are able to go into this, but they need the right incentives, not so much on the cost, but on the some kind of security for bringing in projects. So whom are we talking to in this project? But essentially we start, of course, here it's not even say, but by the competent ministry in a given country, or the ministry, is it Ministry for Energy, the Ecological Transition? These guys have a lot of names, but that those one where arguments and numbers converge, that then bring a kind of a government to opt in and to go for specific programs along for specific technologies, or that orient really the whole, and define more than orient the energy, not electricity, energy policy. And all at ministry level, there is nobody looking at the power system alone. They are just looking at the energy system, if not even at the whole economy. And we have to touch upon this kind of dimension. Besides that, we have always our friends of the and funders of the European Commission that follow our work with interest regarding the need for CSP now. Power in Europe. We have been talking to all the national TSOs of these countries, and even, of course, with the association. You may know I come from this world, on the TSO side. We have been talking, especially our friends, our partners for research from the research centers are talking with the national financial institutions and funding institutions. I mean, I mix here two things. The financial institutions, or as banks, or supposed to fund industry projects. We have been talking to them, but this is not the main problem for industry to take off. The main problem is again and again the framework conditions, that we have options and calls for interest to the industry that are sufficiently viable for industry to spend the resources on presenting a project. The research, as you better know than I, the research entities, publicly funded entity, are very much depending, and we try to have to develop also a good relation, fluid relations to the funding agencies. We're trying, as our partners are talking to these funding agencies, the national funding agencies. And of course, after having talked to the ministry, now it's never a surprise to hear from the regulating entities that two things: one, that they cannot go against energy policy of the country, first, and two, that they have their own consumers. They defend the interest of their own consumers. The civil society sincerely, and NGOs for the time being for CSP has not been, we have, of course, even before the project, we have a lot of alliance in Brussels with various, associations and entities trying to mobilize the civil society, environmental groups, and things like that. But as strong as this was for the PV world, for specific reasons, power to the people and things like that, this does not play, or would not play today, a similar role for larger industry infrastructures. So what the project, what basically the flow chart of the project, understanding, trying to work out matches, or the suggesting and developing ideas, matching what we heard by the rulers, let's say, or the ministry of the various countries, and then we had indeed, all this is now by online, but we had a lot of meetings with national and main stakeholders, officials, especially when we close a given project. There will be a national event when and the outcome, what can this outcome be? We will try to say, again, country by country first, look, there is either this research capability, this industry, and this potential. Now, the needs, by that, what we hear from the TSO, what we derive from your energy, from national energy and climate plans, especially your objective there, this leaves the door open for some contribution by this concentrated solar technology. The point is that if you want this contribution to happen, you have to provide to industry, as I said, to open doors, and this has a lot to do with the criteria, with the design of auctions as they are today organized for not only for CSP, but this technology focus only, let's say, LAOC based, LCOEs, yes, based auction design. The cheapest is the best, and this is not in reality far from being the optimal method for building up new capacities. So, and this is just the first part. With this, I would close, let's say, I don't know, Simona, now the presentation of the project, what the project, what it does. And we, as you heard, we are very far away from screwdrivers and technical stuff. We are essentially in policy making. We can now, I can give you, if you want, I don't know, let me know, Simona, if this is okay for you, or I could give you a first view on what we hear, what are the first findings, what are the first results, even temporary results of this work so far. And there's I put it in 4 or 5, I don't know, very simple points. Should I go on with that?
And then open the discussion. Yeah, to have some questions. We do have already 2 questions to answer, a couple of questions from all the panelists, but maybe we can, I'll take the opportunity also to before to go with your open question, Marcel.
Yes.
I would like to answer just to a couple of questions. One of these that was all of plans that we have show today. I mean, mostly maybe the Italian ones, on Moroccan one. They ask if they are hybridized with the biomass, and the answer is not. Not these new ones. The other question is from Luca directly, and I know the Spain. We know that, you know, in some European country, fortunately, the policy, you know, it's so the National Energy Climate Plan include the target of a strong target like Spain of including the updating the new project for CSP, of course, by 2030. Especially the 5 gigawatts of Spain. I mean, of course, for us was very interesting. So Luca was asking, will this help opening the doors to new projects in our continent? Okay,
Yes.
let me also add, Marcel, to you. We are experiencing now this renewable energy auction in Italy, in Portugal, and in Spain. No one of these was focused on CSP. At least that 3 different kind of auction scheme. But anyway, none of these are targeting CSP. Mostly it's PV and wind technology, I must say. Like in Italy, with these, they said that the decree, the ministerial decree that launched this auction scheme, they say that this was more for most mature technology, no? So really, as you said before, less pay as you bid. So less you offer, better you will be in the ranking. But there will be another decree for the less mature technology. It can be CSP or actually also of some offshore or geothermal. So this is also a possibility, I would say, for Italy. We will be interested to listen from you the experience for Portugal, and we will all waiting for the new auction scheme, maybe by the end of the year in Spain, targeting more than 15 hours of storage, so which means naming CSP. So, Marcel, this is just a summary, and then you can have your open question. Walter can guide you through also to the end.
Wow. Maybe I can reflect, maybe come back to your 2 questions about, or Luca's question about the expected tendering process in Spain that should be coming out this year. Is this important? Yes. Is this going to have a kind of opening as a door opener function for the CSP market in the Europe, or a new look on the company? Yes, but the essence of the game lays really in the question whether or not this auction will be designed that it leaves a decent chance for CSP projects. But what do I mean? As long as in auctions, you are saying I value the bids according to the best price alone. Okay, CSP is out. You don't need even more. Some of them have in Portugal and also in Spain. There were some kind of first attempts to introduce some assessment terms, if you are, regarding the storage. You know, it's a very fascinating question to define a value for the storage, because it depends on where and how much and precisely. But what we know is that if it's as long or as soon as the question would be about longer term storage, there's something beyond four, maybe 5. This is a question to the industry. If the storage capacity is valued not for let's say short duration, but if you have in the auction something about long-term duration, or even and I will come back also to interseasonal storage issues, this changes completely, because there is a fair understanding that CSP has on bulk storage for long duration has a kind of is not a threat. It would win any kind of auction like this. So this is Spain. This is Spain, and about the symbolic value and the enormously ambitious plan of the Spanish NECP about this 5 gigawatt till 2030. It's in reality it's even beyond feasibility, because it would be doubling the installed capacity in the remaining years of the decade. This is too nice to be true, but it would have clearly, for the whole sector, a decisive impact. Now, The other country you were mentioning, which is we went into details of the Portugal. Portugal has put not 5 gigawatt in its NACP, but had put, and it's nice enough, 300 megawatt in the plan. And we had a lot of talks with ministries and TSOs again, and to try to get to bring it to the point what is really the intention. And also this deeper analysis revealed, and here I can if you want I can go back to my
Yes.
to the slides I prepared, is
Yes,
that
yes.
Portugal, as nearly all the countries, he said, well, electricity stemming from CSP is probably a solution, or the one of solutions to integrate more wind and PV. It's according to what you said. It is, but so it is kept in the radar. Let's say it is kept on the. Nobody says, well, forget CSP. It will never happen. It's dead technology. But in Europe, this is the ministry are looking at what is happening around CSP, but they this is backed immediately by another firm statement. TSOs do not see this as a priority now, and I put an additional line that this what I just said about CSP electricity in Europe is more than probably, is definitely looking different compared to Morocco. We heard the example of Morocco, and we know a little bit more also about what brought the deployment of CSP in Morocco. So I'm talking now in this context more about European countries. So one is that not forgotten, but two is not now. There is too much of interconnection in Europe. The capacities are enough on the European system. So with exchanges and contracts, we can deal with this with the balancing of the network, even in situations when you have up to 30% of PV and wind in your system, and a large part of this is going now out at sunset. TSOs know how to manage this now, and they say, well, let's look in 25, 26. Well, what would be the best solution? It is this timeline element is key, so that we have to provide. Also, having heard this, we have to provide arguments and to lobby, if you want, so on the government to say, well, guys, but if this is not now a priority, but if you have to have in 5 years the capacity at best, let's say, cost or the available, then something should happen for the industry and for this sector right now. So I'm sorry. Even talking about Portugal, we have done a special exercise as not performing on the Portuguese with our partners, of course, not the small Estella, but we did a kind of study using what is called inductive project planning, and we have tried to, based on real data, officially available data about generation demand as they are provided by the TSO itself or by also national Portuguese associations, how to look where is the optimal, what is the best impact on the power system, on Portuguese power system, of changing the generation fleet among the technologies used. And to make the story simple, this result, the most striking result of this exercise is that if you increase, also if over the next years of the decade, you would increase the planned investments in renewable by something like 7 or up to 10%, which is, oh, everybody says, oh no. But then the immediate impact of this is there would be a reduction of curtailments of those renewable, of wind and PV, up to 50 and more percent. So a little bit more investment brings a dramatic reduction on curtailments of these capacities. And this is at the moment a very important discussion to which extent let's say the increase of curtailments according to a further increase of variable or intermediate, call it as you like, as a wind and PV in the system, is how far is this going to go before this will be also an impact on the investors' appetite to continue to, will investors continue to invest in wind and PV where you are at 2 point something, as sometimes it appears to be, as when the costs are so low, and you know that 10% of this power is going to be curtailed, or if you and so this is a very interesting. We have not finished here the analysis of things, but we have on Portugal a very specific, let's say, approach to even the benefits, let's say, that Portugal economy would draw from not only 300 megawatts of CSP, but the model results in a kind of optimum something up to 600 and beyond. 600 megawatt would deliver the best. There is not one solution, but this is a kind of dozens of solutions are possible. But this is in this range that CSP would make sense in Portugal. But all this being said, the common denominator of policy makers on the continent is saying, well, all this is nice, maybe soon, but we're looking at it. The industry should demonstrate, this is this chicken and egg. The industry should demonstrate that CSP can play, can improve and can improve performance and lower costs. But the first thing that we hear from the government is say, show us what CSP and the whole chain of value can do beyond electricity in the context of decarbonizing industry, and maybe also in the context of production of new fuels, because as everybody here in the audience has understood, of course, decarbonization of the power or the energy system is the lower hanging fruit if you compare this to the decarbonization of industry processes and transport. So, and the last keyword for me is that this is also the reason of the giant hype, I call it. It's more than the fashion, it's a fascination for hydrogen industry, because governments are seeing, besides, of course, no markets and no business opportunity, there hydrogen would serve marginally maybe the electricity system, but could play a much bigger role in the context of decarbonization of industry and mobility, let's say future mobility issues. So
Marcel,
yes.
we need to conclude because we are running out of the time.
This is the last one. It says we have the need is for fair and supporting framework conditions. As I said, and in order to do that, we have to hook. This sector has to hook on maybe into first niche markets in the strategy by the big players, because what is perceived, this is my last word, but what is perceived as a national interest by the various countries is not the product of analysis or modeling stuff, but this is also the product of looking at your main player and your national champions. So I will close for that and probably take some questions or try to give you some answers to my question, to other questions, right?
Thanks, Marcel, and I will give you the floor to Walter to moderate this with the last message that no single fuel or technology can enable the entire energy sector to reach net zero greenhouse gas emission. So success depends on a deployment at scale of a wide range of low carbon solution technology, tailored to individual part of the energy sector and to country-specific circumstances. So thanks to all of you, and thanks, Walter.
First of all, I would like to answer to the question submitted by Amaya. No, the CSP could be integrated with the biomass or gas, but a lot of the CSP plant use only the solar energy. Depend of the position of the plant, obviously, but also the energy politic of the site where is built the plant. For example, the plant in Morocco use only the solar energy. The Spanish CSP plant using only solar energy. In Italy, it was chosen this different solution, also because it was used for the first time in the world to molten salt, both in the solar field, then for the storage energy. Then I go to the conclusion. And first of all, I would like to thank all the speakers for your nice, interesting presentation. I would like to apologize with the audience about some technical problems, but all the presentation will be available in website ENEA at the site linked with this event. And regarding the CSP, what I can tell. CSP is ready, CSP technology is ready to give a hand to reach the ambitious target of the Green New Deal set by the European Commission. The research is already developed the commercial solution. These commercial solutions are running in a real commercial plant, but in the same time, the research activity, the research and development innovation activity supported by the European Commission and the single country are developing the technology for the next generation of the CSP. Regarding the development at the commercial level, also because the targets are very ambitious in this field, we need also to change the energy politic of the single country, but also the Europe, to interconnect all the country with the green grid power, where the CSP with its storage system can give a very important hand to solve the pending question. Now, I would like to thank the audience for the patience and also for the little delay in the end of this webinar. And that's all. Thank you very much.